for the initial notes. Today, we are going to do a session on time series analysis of streaming data. Um, for the introduction, my name is Aurobindo, and I work for the data practice. Along with me in this session, I have also Aditya and Roshni, who has helped me to get the demos set up. And they are also working on the streaming analytics for some time now. And rest of my background information are visible on the slide. All three of us work in the big data space, and streaming analytics is a specialization of big data computation. So we're going to talk about the streaming analytics today. Let me quickly check if my screen is not shared. Give me a second. Yeah. Okay. Well, sorry for that. Yeah. Thank you, Roshni, for letting me know. So I hope now it is visible for all. You can see our introduction. Okay, can if someone of you can respond yes or no, yeah, that would be great.
Yeah, we
Okay, great. Okay. So unfortunately, I don't have a visibility to the chat window. So what I have requested Roshni and Adi is to keep a note of the chats or the questions that are coming in. So feel free to post your questions at any point of this session. But I will look at your questions after an hour when the demo will start. And I will start answering your question in the last 10 minutes of the session. But for the first 1 hour, I would like you to request to go on mute. But yeah, put your question on the chat window, please. Okay. For today's session, we are going to take it in 4 steps, basically. I understand many of you might have some background around big data or streaming data, but I tried to start the session with an assumption that some people may not have that background. So we'll talk about what is streaming data, and in particular, you can do many things with the streaming data. And in this session, we are just going to look at the time series analysis, the analysis that happens on the time scale. And as part of the time series analysis, one of the modeling techniques or organizational techniques for storing and querying and transforming and analyzing that data is windowing. So windowing is one of the very key concept that we need to understand for time series analysis. Then we are going to take a deep dive in the technology, and I have picked up some of the technologies that I have. Just give me 1 second. I get a ping from somebody. Just wanted to ensure. Oh, okay, great.
Hey, Guru John.
Hey, Guru. Thanks for joining. We have about 94 participants today. We have just started with the agenda. As part of the technology deep dive, we are going to talk about these 4 technologies. There are many more technologies in this space, and the reason we picked up these 4 is we have done some POCs in last 2-3 months, and we use these technologies, and we have a deeper insight on these technologies. And lastly, we're going to take you through a demo and answer your questions. Okay, fantastic. Let's start with the concept of what is streaming, right? So if you look at the data analysis space, it's going through a huge revolution. I mean, so far we have been looking in analyzing data, small data, big data, whatever, in a batch mode, right? So when I say in a batch mode, the data notion of data was having a boundary, right? So it can be a boundary of hours or days or end of month processings, right? But it is a bounded data stream that we have seen so far. When we go to streaming data, we make an assumption that the data flow never ends. It may start at a particular point of time, but it keeps on continuing, right? And that brings lot of complexity in terms of how you can visualize or understand that data, because it is a free flowing data at any point of time. And here are some of the examples like credit card transactions, all the IoT measurements that we get maybe from the weather stations, machine logs, and there are many, right? So this concept of unbounded versus bounded data stream is a game changer, right? And the technologies so far that had been developed has been around the bounded data streams. All our ETL mechanisms so far had been around bounded data streams. Even the futuristic technologies like MapReduce, or even if I talk about Core Spark, those were also handling bounded data streams. Now, from Spark streaming APIs, and there are a few more technologies that you saw in the previous slide, we are understanding how we can handle unbounded data stream. So one of the key challenges when we handle unbounded data stream is something called a state management, right? So what does state management means? State management means that when we try to analyze any point, uh, I want to store at what condition that data is in, right? So if I am analyzing at, say, at an nth time, what is my rolling average, right? I want to store the state of my computation so that so if and this storage, as we understand, there can be many such storage, and individual tasks, the logics, the states are getting stored either on the disk or mostly on memory, right? And this storage helps in fault tolerance. And why do we need to worry about fault tolerance? The reason is uh, we have to depend on multiple machines to carry out these kind of streaming computation. One machine won't be powerful enough, or one machine is not good enough to do this kind of computation. So when we're talking about multiple machines, we are talking about network, and we have to make an assumption that network can fail. Or not only network, a machine CPU or RAM or disk, any of these can fail. So in order to revive from that state, state management, and in particularly what you call stateful computation, is extremely important. Um, because you are never going to get back that state because the stream has already flowed, right? So you have to do checkpointing to save your state. The other concept of around consumptions and consistency guarantees of stream is when you deliver a stream or a stream from one source to another, right? From one place to another, and we typically call it a source and sink, right? Uh, what is the guarantee that that packet has flowed to the other side? Okay, and these guarantees, there are three kinds of guarantees, as you're seeing. One is called at the most, next one at least once, at the most once, at least once, and exactly once. Now, as the name suggests, right, at least once makes a guarantee that it will deliver once, but it may deliver multiple times. And then the problem of duplicate data arrival uh, uh, may happen, right? So it says at least once, but it may deliver multiple times. At the most once, it will try to deliver at least once, but it doesn't even guarantee whether once it is delivered. And lastly, the most complicated one, which is very difficult to implement, is exactly once. So there can be multiple consumers on the receiving end, which is waiting for the message, right? Now, exactly once is a very difficult um, uh, consistency guarantee to achieve. Okay, I am getting some questions. Let me quickly check. Okay. Some people are unable to hear voice. Okay.
All the participants are requested to please, open the same link and, close the Skype meeting that was opened, existing one, and also to mute themselves, please.
Okay, thanks. Okay, so I assume others can hear my voice. If you can please respond yes or no on the chat window. Okay, okay,
Yes.
great, great. Thank you. Uh, let's proceed. So far we have discussed about streaming data and trying to understand what is exactly streaming, and we talked about unbounded data, state management, and the consumption consistency guarantees, right? These are very high level topics. Let's dig a level deeper and try to understand when we are saying time series analysis, that's one of the many kind of analysis that you can do with streaming data. What does time series analysis mean? And this session is only about time series analysis. Um, so time series analysis means that there are a series of data points that are captured at different points of time, and these can be in the range of nanosecond, millisecond to even hours, days, or weeks, or months, right? But these data points are captured, okay, and typically these are your like measurable data points, like something that you can sum upon, or numbers, right, or average upon, right? And then you arrange these data points uh, on a time scale of your choice, right? So you might capture these data points at a millisecond level, but your requirement may ask you to represent them at an hour level. So there is a roll up happening. So these kind of analysis is time series analysis. Now, why are you doing time series analysis? And there are two main goals. One is, as the stream of data flows in and as I arrange them in a time scale, I'd like to look back and understand what is the nature of the phenomenon represented by this sequence. So is there a rise in the pattern, a drop in the pattern? How is it looking like, right? You kind of look at the rear mirror and see what has happened, right? A typical business intelligence case. But the most important piece is, by inferring, looking at this data, if you can forecast the future, right? So for example, by looking at the fluctuation of the commodity prices uh, at the historic data, can you predict the future prices? um, and we have many POCs around that. And in one of we did a sentiment analysis on a crude oil pricing. So we took different news agencies data from various websites and interpreted the word and tried to map it on a time scale to see if you can predict the crude oil price, and it worked to some extent. Okay, so let's go to the next
पढ़ाई
one.
करते ना मम्मी,
And
काम चल रहा है
uh,
मम्मी का, काम
request
खत्म से लेके जाए.
excuse me, I'd request everybody to go on mute, please. And yeah, go ahead and put your questions on the chat window. I will look at it later. Okay, so as I said, windowing is one of the key modeling concept when you do the streaming, right? And we're in the next like 10 slides, we're going to dive deeper to understand windowing, right? So this is a series of data, and these are the different events that are happening. Um, the way we can boundary this data for our analysis is either by timescale, or we can make a boundary based on number of element or number of events we can count, right? So for example, here, if you look at the one below, we are counting 3 elements and making the windows. So the length of the windows, when we do it by element, may be uneven from a time standpoint, but equal in the sense that the number of elements is exactly 3. Um, and sometimes it is a combination of both. So
Participants are
time,
requested please to mute yourself.
okay, thanks, Bank. Okay. Sometimes it's a combination, right? And in some cases, the logics go very, very complicated. For example, in the first time window, I want to make a window if the number of elements is 3. In the second time window, I will consider it a window if I have a custom defined function and certain conditions is satisfied, and then I call it a window. So the point I'm trying to make is, the way these windows get formed generally is on time scale, generally is on count scale, but it can be far more complicated making a combination of these two, or having a user-defined logic to build the notion of the boundaries on the streaming data or create windows, right? So let's talk about the simple windows, okay? And then let us see how do we implement it. Today we will not go into number 3 or 4, but we will look into number 1 and 2 and try to understand how different technologies can implement it. The tumbling window is the most simple one, and it is a non-overlapping window. So the way I'm going to take you through this is with an example. So here is a street, and there is a sensor hanging on the top of the signal that counts the number of vehicles passing, and it counts every 15 seconds. Okay. So these are the counts that the sensor has done. So these vehicles are passing out. So first it has measured 2 vehicles, and then in the next 15 seconds it measured 3 vehicles passed, and the next 15 seconds it measured 1 vehicle, so on and so forth. Now, the nature of the streaming data is that the data is continuously produced, right? It keeps on growing. So how do you going to calculate a final sum? I mean, there is no way you can stop this data and say from this point I want to calculate the final sum unless you define a window. But even before I define a window, I can come up with a simple logic that, okay, I do not need a final sum, but I want a rolling sum, right? So basically you keep on counting whatever has happened on the previous event. So first 15 second, two vehicles, then at 30th second, I get 2 plus 3, 5, and so on and so forth. So you can do a rolling sum, but still rolling sum is just like the streaming data that was produced from the sensor. I mean, there are no boundaries. It keeps on flowing. Yeah, these numbers are just an addition of the previous numbers, right? So if I look at the tumbling window, which is the simplest form of window, I hey, sorry, my voice was disconnected. Um, I think I was kind of mute on these slide, and this is very self-explanatory. All I talked about is a rolling sum. Guys, can you hear me now? Let me look
Yeah,
at the chat. You can. Okay, my apologies. So
yeah, we can hear you, and we hear these slides also.
oh, okay. Thank you. So I was talking about the tumbling window, and the notion of tumbling window is basically you have a contiguous windows, but here we are creating a boundary one after another, and we said here that it's a 1 minute window, right? So that's how we got like 5 elements that makes 15 into 4, 1 minute, right? And then we are outputting the sum for one of these. For each of these windows, these are tumbling windows. Let's get into the concept of sliding windows. The sliding window is basically so let me again reframe my question. So I'm saying here is you continue that uh, count for a minute, but you trigger such counting every 30 seconds. So in the first case, so ignore this, there were a few more which vehicles has passed, but here at 45th second I started a window which went up to this, like 4 elements got captured. But during that 1 minute here in this orange box, at the 30th second, right, I started another window. So these two are like parallel series of window and kind of tumbling. So these are kind of hopping. So the difference between this window and the one previous here, the orange one and the yellow one, is 30 seconds, because my way of analysis is you look for a minute, but you trigger windows every 30 seconds, right? So in this case, what we are doing, we are, I mean, these colors are self-explanatory. We are kind of outputting the sum from a sliding window, and we can do sliding in different ways. And this is the most simplistic way how you can kind of do a slider, move the slider a bit, in this case 30 seconds, but the length of the slider is fixed across the different series. Okay, this concept becomes more interesting because in practical world, if I talk about multiple sensors, right? And there we have to keep a notion of a parallel window. Now, the earlier case, why we are saying that it is not a parallel window, it's so these are all non-parallel windows. In a sense that one machine or one processor has to compute this, because it has to have a notion of the previous series of window, right? Um, but if you have multiple sensors, now each of the measurement from each of these sensors are independent of each other, right? So sensor one, or in this case, let's say, yeah, so if you look at the series, the first element is your sensor number, right? And the second element is the measurement, right? Number of vehicles passed. So if you look at the series, so I have taken the third sensor is here, and then I go here. The third sensor is here. So if I look at the series, I am putting the third sensor in machine and in a different machine from where I put the first sensor measurement, and from where I put the second sensor measurement. So these three sensor measurements can happen uh, in parallel, and that's the concept with which you can achieve parallelism while doing windowing function, right? Okay, so much so far we have talked about different concepts, okay, and there are other windowing concepts. There are concepts of evictors. There is a concept with which where you do not talk about time, you rather talk about the number of elements, right? We'll come to those gradually, but let us now look at a kind of a code and try to see exactly how it is done while we implement in a program, right? So we said we have done most of these processings in Flink. So Flink would be our main focus. And then we will see how it is done in SQL. Okay. Okay. So let's look at the way we do it in Flink. Okay. And so if you look here, what we're doing, we have a streaming as a variable for your vehicle count, right? We have a stream of vehicles counts. And then we have defined a variable where we are applying the time window API, and based on the number of parameters we pass. So here we passed one parameter, which is in minutes. So every minute you count. So by default, this makes a tumbling window, the one which is one after another. This one, right? Contiguous fixed length windows. So this will give you a tumbling window. Whereas if I use another, a window length of 1 minute, but you triggered this every 30 seconds, which is the second case which I explained. Now this is by actually explain a use case that we had done. Okay, so let's understand the use case. In fact, we had one of our project about 2 years back. So what was happening here is something called smart right? So what it does, so this diagram is talking about what is happening today and what will happen in future. So the notion is very simple. So there are three parties involved. One is the consumer of the electricity. The second are the people who distributes the electricity. They're the utility company, right? And the third one are the people who generates the electricity. Now, most of these use cases are either for the utility company, and sometimes some of these use cases are for the consumers. The whole idea is these utility company has to predict the amount of energy needed in coming few months or days, okay? Because if they cannot predict that energy demand correctly, they have to go to the spot market to purchase energy from these energy generators, which is very costly. So they want to make a good prediction so that they can kind of block certain amount of energy for coming days. So these smart meters communicate to the utility company, sending the amount of energy required at millisecond level. Okay, not required, the amount of energy spent. So take for example, I am running a washing machine or a high energy equipment like an air conditioner. Versus I am running a low energy device. So if I can let my utility company know what is my usage pattern, they can kind of shared the load at different times of the day and say, hey, if you run your air conditioning or say the dryer at certain period of the time, we can give you a better rate. Okay, so there is a customer engagement use cases also, as well as the load distribution and demand distribution use cases as well. So in our case, let me show you the data that will explain it clearly. Give me a second. Let me pull up this Excel sheet. Okay. Okay. So ABC are my raw data. We'll talk about this later. So we have a date field, and for the simplicity, I have just the amount of milliwattage and then the house IDs, right? And for sake of simplicity, we have kept. Okay, sorry. So we have kept only 20 houses, right? Now, what we did the first thing as part of our data curation is we converted this epoch date into our normal date and time. And if you see the time, we are counting every second, okay, for different houses. A special attention house number 11 because it appeared at 3:30 or 1 second. And next time it appears after 20 seconds down the list. And there is a particular reason for house number 11. I'll explain that. So this is how my data looks. Now, if I want to implement it in a time tumbling window fashion, right? And again, think these as my parallel windows, right? So you remember that I talked about the multiple sensor IDs and we can parallelize that. Exactly, that's what we did. But for the sake of explanation, let me pick up only house ID 1 and try to explain this. So house ID 1 is emitting data at every second, and I want to apply a tumbling window of 5 seconds, right? So contiguous window one after another, and you can see these are just some functions applied on these data, right? So this is how my tumbling window should look like. If I go to the next slide and talk about the sliding window, so some people might be wondering why this one is smaller. It's all because of the offset and the data starts before that. So pay attention to these windows, right? The one after the first one. So anyway, so here we are talking about a window length of 10, okay, but hopping over every every 5 seconds. So that's why I have kept these numbers in bold so that you understand why it triggers, right? So 16 should be bold. And then there is a sessionization, and that is the reason why we have 11th number element. In the sessionization, what we have done is we are saying that for a session will start if the gap between subsequent counts is more than 10 seconds. If you look at the house ID 1, the emission is happening at every 1 second, so it's all one session. And that happened everything all the way up to house number 10, right? But in case of house number 11, the first emission happened on 3:30:01 and the next one at 3:30:02. Similar amount of usage, which is fine, but the gap between these two emissions is more than 10 seconds. So these should be 2 sessions. So let us look at how this happens in the code, right? Okay, so I have a bunch of input functions, and then if you see here, first of all, let me show you, I read the data from here, right? The similar kind of data that we have. It's under resource from this data, right? So exactly the same data. And going back, okay. So what I'm doing here is I'm applying different window functions, and it is little different. The last one which I showed was the number of elements. In this case, we are using a dot window API where you pass the type of the windowing function and the elements. And after I run this code, right? So let's run it. It will be done. Okay. So you get a set of things. So let's look at the tumbling windows. Okay. And because I have looked at this code earlier, I know the third file has house number 1. So if you look at the house number 1, it has 7054, right? So go back to the tumbling window. 7054 is my summation. Next one is 16808. Okay, here is one. But before that, here is one, line number 4, 1608. So on and so forth. And I will share this code. You will get these files. You will understand. And I personally have verified all of these sliding windows, tumbling windows are working fine. Take, for example, let's spot check the sliding window, right? When we said, let's look at the code, the sliding window code here, right? We have 10 seconds and 5 seconds, right? Go back here. It's 29,990. And if I go to sliding window, 29,990, right? So, and the rest of the figures also matches. The sessionization is interesting because in the session, what we're going to see is each of the file you see one output per house. But interestingly, look at the fourth file. Here, we get 2 output because these are 2 separate sessions. These happened more than 10 seconds apart, right? I have put 10 seconds out here for the session windows. So that's how it happens in the windowing. Let me get back to the slide. Okay, so far so good. So we can go a level deeper and try to understand exactly Flink's mechanism of doing these window assignments, how this happens. Okay, so on a high level, okay, so every element, okay, that flows gets into a window assigner. The window assigner assigns these elements that comes into either one window or it can go to multiple windows, right? And if you look at the window assigner, it is nothing but a storage of metadata of these window information. Now each window has something called a trigger, and that trigger decides when the window will be evaluated or purged. Okay, and so a trigger just fires a trigger just fires the so what will happen sometimes there, whenever a trigger fires, right, on an insertion of an element, right, it can either go through an evictor. Evictor concept is like you are discarding certain elements from the beginning of your window. Sometimes that logic is required, and this is an optional thing, right? You can use a evictor if your requirement required so, or you can skip the evictors and go directly to the evaluation function. And these evaluation functions are typically aggregation functions, like I have mentioned, and or there can be other fold functions or windowing functions. Other functions can be applied. And so this is the notion. I have notes on this, so and I have a link on this. You can go through it in more detail. But for the purpose of this session, I won't go into further details of this. But these are the main components in which Flink's mechanism works. There's a window assigner. The windows are formed. Window assigner basically stores the metadata of the window. There is a trigger attached with every window, and the trigger fires on insert of every elements. Each of the element is then passed for evaluation either through an evictor, or it bypasses the evictor if there is no need of eviction of initial elements, and it can directly go to the evaluation function. Okay, so far so good. So we have talked about some of the SQL way of implementing it, and the reason I kept this section is many people are familiar with SQL. I will not go into every details of every slide. There is no demo with this SQL, but just few things here, right? So if you look at the SQL way of doing it, the syntax is you use something called a partition by, a over, and order by, and rows. So let's understand what are each of these. So think your time data as a set of data, right? And the first thing that you do is kind of group by that data. Say it will get group by minutes or group by hour, right? So first thing is you partition that data, and then you order each of the partition by certain some columns, and it will become apparent if you look at this thing, right? So in this example, what I did, the timestamp, I'm partitioning by the timestamp, right? And I didn't use, yeah, I used order by, and you are ordering by timestamp. So these are the two things that you require. Then you can also mention as an option field within that partition, each of this partition, what are the rows you are considering, right? And then you can run some function on top of each of these partitions. Let's look at some of the examples, right? So here we are running a lag function, okay? So in this case, we are first taking these two, the first two columns, and what lag function does, I'm lagging it by 1. So this element comes here, this element comes here, this element comes here, this element comes here. So it's, and if I lead it, basically this element goes here, this element goes here, and so on and so forth. I can do a count, I can do a sum. So if you look at a count, basically if I lag over timestamp, so this counts are increased because 1, 2, 3, 4, that's how it goes. But if you look at the sum, it's like 1 plus 2, 3, 1, 2, 3, 6, 1, 2, 3, 4, 10. That's how it proceeds. Very simple example. I will let you go through the other examples. This is rolling average. This is how it happens over multiple partitions. I've got a tag and I'm partitioning it by the tag. Next one is a practical example how you want to do a partitioning with different types of houses, right? So I've done the partitioning by the type, and then I am calculating the function I'm applying is a row number, and I want to figure out which are the lowest priced homes. So I use row number less than 3 to do that. First I do the ordering, and then I take only the ones which is less than 3. And here is an example for clickstream sessionization. So typically used in the website user behavior analysis. So if you look here, I'm trying to create a session and define a session. And if the sessions are coming from the same IPs 30 minutes apart, I call it a new session. So if you look at this IP 102, each of these sessions are all within the same time except the last one where it is more than 30 minutes apart, right? And that becomes a new session. So, okay, I will skip this part. So the third part which I wanted to talk with you is the similar implementation function using Azure Stream Analytics. It's very simple. I mean, these are self-explanatory. We talked about tumbling. This is just the syntax. How do you do that, right? You just put the time. You just put the it's measuring in seconds and what is the size of each window, right? And similarly, you can define a hopping window, okay? And then you also have a sessionization window. So you have different. So most of these tools will be able to give you the windowing function. Okay, let me quickly do a time check. We are about 40 minutes through. In next 20 minutes, we are going to do a technology deep dive. And we are going to talk about 4 technologies here. And my intent was to go to Flink in depth and talk about overviews of Kafka, Cassandra, and those things. So let's see how far we can go. And there is another interesting technology called Druid, D-R-U-I-D. We'll see how it works here, right? Okay, so Kafka is a technology which is generally used as a stream producer. So what does it mean, right? It also is used as a consumer, of course, but we typically use it as a queue, as a streaming queue, from which a transformation technology like Flink will read the data. Okay, but again, it's at the beginning of your pipeline, right? So what does this word producer, Kafka producers means? What does the broker means? Let's understand that, right? So in Kafka, the concept of broker, for simplicity's sake, think these as separate servers, right? There are multiple brokers. Think these as servers. And when you talk about topic, think it as a table, right? So what happens, you can take a topic and break it into partitions into multiple brokers. So look at this diagram. So you take a topic, this topic 1, you're breaking into partitions, and inside a partition, each of the elements are ordered. That is guaranteed. and there is an offset of which particular element has been read, right, or written. And there are replications happening between the brokers, so that the topic one, partition one, is replicated in another broker. In case broker one goes down, the other broker can pick it up. Okay, so that's the concept. Is similar to a database world where you are taking a table, splitting up into multiple segments and storing data redundantly across multiple machines. On the consumer side, okay, on the consumer side, um, there is a concept of consumer group. So consumers are the elements which read these topics, right? So the multiple consumers can club together under something called a consumer group. But there is an interesting feature that within a consumer group, a consumer can read from uh, a topic partition, like consumer one is reading from partition 0 and partition 1, and consumer 2 is reading from partition 2. So consumer 2 cannot read from partition 0 or partition 1 because it is already been read by consumer 1. So it's exclusive. So these readings are exclusive to individual consumers within a consumer group. So that's how we define the Kafka side of it, right? There are a lot of details to it. There is a 4 hours video. I can share the link. I think I have it in the reference section. It's a wonderful video to get an overview of Kafka. Now, this technology piece, Kafka, okay, if you see, we typically attach the Flink on the consumer side, right? So let's look at Flink. We are just give me 1 second. Your screen is not shared. Okay. Let me try to share again just in case it's. Okay. Can you see my screen? I am at the Flink concept slide.
Yeah.
Yes, we can see.
Okay. Sorry, at what point did we lose the screen share? Could you see the Kafka concepts there?
Yeah, right.
Yeah, we can see.
You saw that. Okay. Okay. Maybe after that we lost it. Anyway, so let's talk about Flink. Right? So Flink has excellent documentation, and these are the different conceptual document points that I read in the documentation. Um, so So if you look at the different levels of abstraction, Flink has a low-level APIs which gives you the immense power of doing various kind of transformations, right? But on top of that, under the low-level APIs, we call it stateful stream processing APIs, right? You have something called core APIs. Many people call it candy APIs. So these are basically ready-made APIs, like the way you saw for the tumbling windows and those things, right? And keep in mind, the Flink can also do batch. That is very interesting. I mean, Flink is inherently built for stream processing, but even if you think about batch, it is nothing but a bounded stream, right? So Flink can convert a endless flowing stream into bounded streams and do batch processing. Okay, so the way Flink do it is they call it data sample here between the source. The stream is already partitioned, right? So the map function flows one-to-one. But in some cases where you are doing, say, key buys, there are shuffling happenings across the network, and the information has to travel across multiple machines, right? So yeah, it supports parallelism. And interestingly, some of the observations we did is when we tied up Flink with the Kafka, there were scenarios of back pressure handling that was very well handled with Flink, right? So the rate of data flow from Kafka and the rate of data processing in Flink, that is very well coordinated. So Yeah, so we really found Flink very powerful. I think Windows we talked in various length. You saw how it is being implemented in Flink, so I will not go into details. Okay, so here is an interesting concept of time, right? So we're talking about time series. Everything revolves around time, but what is exactly meant by time, right? Where is that time? I mean, where